start. In this example, we're going to look at several ways to estimate partial derivatives. In the first part, we just want to decide if the partial derivative is positive, negative, or zero at the point r, if each partial derivative, so the partial with respect to x and the partial with respect to y. And we were given a warning that the view's been turned a little bit, so we should pay attention to our axis labels. So first, let's think about the partial derivative of f with respect to x at the point r. So what that means is that we're walking through r, but along a trace that's parallel to the x-axis. So I'm walking through r along that shaded green path right there. And then the question is just like it would be in one variable calculus. Are you going uphill? That's a positive derivative. Downhill, negative derivative. Or the top of the hill, bottom of a valley, that's zero derivative. Well, as I walk in the positive x direction through that green arc, at the point r, I'm at the top of the hill. So that means that the partial derivative of f with respect to x at the point r is zero. Now let's think about the partial derivative of f with respect to y. Well, that means that we're walking through a trace that's parallel to the y-axis that goes through r. So that means that we're going in the positive y direction on that purple shaded curve. And as you move in the positive y direction, so parallel to the y-axis through the point r along the purple curve, you're going uphill. So that means that the partial derivative of f with respect to y at the point r is positive. In this example, we're going to look at a table of values for f of xy around the point 2,1 and use it to estimate the partial derivative of f with respect to y at the point 2,1. So we can see that since we're looking at the partial with respect to y, x is a constant. So x is always going to be equal to 2. So x is always going to come from this red column because x is always equal to 2. And then we're allowing y to change a little bit and seeing what's the change in z, change in f of xy, based on this little change in y. So we're thinking about, well, what's the slope of the x equals 2 trace at y equals 1? So we could look a little bit above 1 in our table, so we could think about, well, what happens between y equals 1.01 and y equals 1? So that slope would be 3.94 minus 4 over 1.01 minus 1, so negative 6. Or we could look a little bit below in our table. So we could think about, well, what happens if y changes from 1 to 0.99? So that would be 4 minus 4.06 over 1 minus 0.99, so that's also negative 6. So that average, if we take a little step to the left in the y direction or a little step to the right in the y direction and see what that slope is, that average of those two numbers is a really good estimate for the overall slope in the y direction. So negative 6, because they were both negative 6, their average is also negative 6. So the partial derivative with respect to y at the point 2,1 is about equal to negative 6. So what we did was we kept x fixed at 2, and then we said, well, if y changes a little bit in either direction, what's that slope? And then that slope, as y changes but x stays constant, that's the partial derivative with respect to y. In this example, we have a contour plot for the function, and we're asked to estimate the value of the partial derivative with respect to x at the point 2,1. So we're looking at the point 2,1. So on the contour plot, I located the point 2,1 and labeled it in green. And then, since it's the partial derivative with respect to x, I want to move a little bit in the positive x direction and see how my height changes. So I want to take as small a step in the x direction as possible and to a place where I know the new height. So I'm going to move in the x direction, parallel to the x-axis, to the very next contour that's marked. So I can see that that change in x is about a half. I went from 2 to 2.5, and the contour changes from the contour 10 to the contour 12. So the partial derivative of x with respect to x at the point 2,1 is about the change in height over the change in x as I move in that x direction along my contour plot. But I need to take as small a change in x as possible, so that's why I stopped when I got to the very next contour. So that change in the contours, the change in height, well, I went from 10 to 12, so 12 minus 10. And then 12 was the height at 2.5, and 10 was the height at x equals 2. So if I do 12 minus 10, then I need to do 2.5 minus 2, and I get 2 over 0.5, which is 4. So I think that the partial derivative of f with respect to x at 2,1 is about 4. And notice that as I move in the positive x direction, I'm moving from contour 10 to contour 12, so I'm definitely going uphill, so I should get a positive answer. And that's something that's really easy to check, so it's a good idea if you're estimating the derivative with a table, with a contour plot, or even with a picture, that you think about the positive and negative aspect of the derivative and just check, am I going uphill or am I going downhill? Because if you're going uphill, the partial derivative should be positive, and if you're going downhill in that direction, then the partial derivative should be negative.